let's talk about elastic potential energy. And elastic potential energy is the energy typically associated with the spring, but it is energy stored in any object that is elastic. So if you, let's say, compress uh, um, a spring, right? So this is, let's say, the equilibrium position of a spring, and you compress it. So that compression will lead to energy stored in the spring. So you have applied a force over here, and that force stores, and through that you're storing energy in the system. So you can also expand the spring, so it can be compression or expansion. So let's say this is the equilibrium position, it can be compression, it can also be extension of the spring that leads to energy stored in the spring. So there is a force that is called the Hooke's force or the spring force. That is the force that a spring applies on an object that is connected to it. So that force is always towards the equilibrium position. So if we go back, so if you compress the spring, it is going to push it towards the equilibrium position. If you expand the spring, it's going to push it towards the equilibrium position. So it's a restoring force, as we call it. So it always tries to bring this mass back to its equilibrium position. So that's why we have this negative sign. The negative sign is to make sure that the compression and that the spring, that the force is always towards the equilibrium position. So if this is your x equals 0, in other words, and this is your negative side, right, and this is your positive side. So you need a negative sign to make the force positive, and then you need a negative sign to make the force negative, right? In other words, because the force is negative on this side, so force is negative on this side and force is positive on this side, whereas x is negative on this side and x is positive on this side. So you see that opposite sign. So we need that sign to fix the direction of force. And I've talked about this a little bit before. So K is the spring constant, right, and its unit are Newton per meter. So K is F divided by delta X. So this is Newton and this is meters, right? So its units are Newton per meter. And the energy stored in the spring is given by half kx squared. So again, this is the x in this case again is the compression or the extension of the spring. So what do you guys think is if I draw a graph between spring versus x, what is that graph gonna look like? What do you think? So yeah, that graph is going to be a parabola because it's it's a y equals x squared type function, right? So that's a parabola. So you can see that this is when the spring is stretched, and this is where the spring is compressed. Okay, so x is negative over here and x is positive over here. So let's answer a few questions about the spring force. So in this question, there's a 10 Newton force that holds an ideal spring, and the spring constant is 20 Newton per meter, right? What you have to find the potential energy stored in the spring. So go ahead and solve the question, and I'll let you know the answer. Pause the video. So the answer is 2.5 joules, and the way you solve this is that you can first see you need to find the potential energy, that's half kx squared. So k is given, k is this, right? But x is not. You don't know the compression, right? But you know that the force that holds the spring, right, is 10 newtons. So force is k times x. I'm just writing the magnitude right now. So that force is 10 newtons, and k equals kx, and so therefore x is 10 divided by k, right? And so when you plug in, and so that's 10 Newton divided by 20 Newton per meter. So that's 0.5 meters. So that's your compression. You plug that into this equation, you'll get this answer. Okay, so let's look at another question. In this question, there is a spring loaded gun, right? It shoots a plastic ball. So let's just draw like a simple picture of what's going on. So there's a gun that shoots a ball. So let's say that the spring is compressed by some amount, right? And the energy in the spring is half kx squared, right? And so when the gun shoots the ball, all of that energy is going to convert into kinetic energy. So the question is, we've been given the velocity with which the ball is launched. So if the spring is compressed by twice, right? If you double the compression, what's going to happen to the launch speed? That's the question. So pause the video, think about it. Okay, so the answer is that the speed is going to double also if you double the compression. And that's because of if you apply conservation of energy, as I said, all of the half kx squared is going to convert into half mv squared. So erase this. Okay, so then if you simplify this equation, you get x equals or let's say v equals square root k over m times x. So there's a linear relationship between v and x. If you double the compression, you double the velocity. Okay, let's answer this question, which is similar. So now the spring-loaded gun shoots again a ball at 2 meters per second, but now the spring is replaced with a new spring that has twice the spring constant. Now you've doubled the spring constant. What do you think will happen to the launch speed of the ball? Go ahead, pause the video, think about it. Okay, so the answer is C. This is a bit tricky one. According to my experience, quite a few students get this wrong, because doubling everything doesn't double the other thing. You have to look at the relationship again. So from conservation of energy, we get this. And so V is square root k over m times x, right? So if you double the spring constant, so in the second scenario where you have doubled the spring constant, right? Doubled the spring constant times x, right? So you see that the square root 2 factor, right? So that you get v prime equals square root 2 times square root k over m times x. So this is your old velocity v. So you get a square root 2 factor. So v prime is therefore equal to square root 2 times v. And so v is 2 meters per second multiplied by square root of 2, you get 2.8 meters per second. Okay, so let me know if you have any questions about this in the discussion.